You might feel quite content and happy with the tensors that we define. But if you just stop there, you're actually missing out a lot, because not all tensors are made equal. In this video, we're going to look at a very interesting, useful class of tensors, the alternating tensors. We'll put on them a binary operation called a wedge product, and under that, they will form an exterior algebra. In the specific case, when these V are tangent spaces of manifold, then these exterior algebras give us a lot of information about the manifold. Alright, so what are these alternating tensors? Well, to define them, we first want to define the permutation action of the symmetry group on the tensors. Let's say F is a covariant K-tensor, and let's say sigma is a permutation in the symmetry group on K variables. Then how should we define sigma acting on F? Well, the result here should also be another covariant K-tensor, i.e. another multilinear function on K copies of V. So we can just define it pointwise. So let's say we have this tuple of vectors in here. If we apply this function to this, what we get is the following. So we just permute these EIs by using sigma, and then we apply F to it. Remember, F of this is just a real number. So this gives a well-defined covariant K-tensor. Let's look at a concrete example just to clarify. So let's look at the case when K is 2. So we have S2 acting on these two tensors. And S2 is generated by the transposition 1, 2. Alright? Now let F be a covariant 2 tensor, i.e. a bilinear map from V times V to R. Then what is the function sigma F? Well, if we input to it a pair V1, V2, then the output should be F of V2, V1, because we permute these vectors according to sigma. Alright, so that's the definition of the action of the symmetry group on these tensors. Now we're ready to define the alternating tensors. So these are the tensors such that under the action of the symmetry group, we should get this resulting function, sigma acting on F, that should be a multiple of F by the sign of sigma. So what does this mean in this specific case? Well, here, what is the sign of sigma? Well, as a transposition, it has sign -1. So we should have that sigma F is equal to minus F. Pointwise, we see that then this must imply that when we interchange the arguments of F, then the sign of F switches. And that actually gives an alternative way of defining these alternating tensors. So these are tensors such that whenever you interchange two arguments, then the sign switches. Why is that? Well, because interchanging two arguments is just another way of saying you're letting F be acted on by a transposition. And Sk is generated by transpositions. So if this condition holds for transposition, it's gonna hold for all the permutation. Thus we can think of the alternating tensors again as tensors such that when you interchange two arguments, you switch the sign of the tensor.